Debye-Waller factor. As the temperature of a crystal is increased, atoms undergo large amplitude random thermal fluctuations with instantaneous nearest neighbor spacings differing by approximately 10% at room temperature. Before X-ray diffraction experiments were done, the proposal of probing the atomic positions with XRD was discussed in a coffee house in Munich. A counter-argument was that the instantaneous positions of the atoms in a crystal at room temperature are far from being a regular periodic array because of large thermal fluctuations. Therefore, the argument went, one should not expect a well-defined diffraction pattern, but such a pattern is found, and the reason was given by Debye. Consider the radiation amplitude scattered by a crystal. Let the position of the atom nominally at R sub j contain a term u of t fluctuating in time so that the instantaneous position of the atom is given by R of t is equal to Rj plus u of t. We follow Einstein model of a solid and assume that each atom fluctuates independently about its own equilibrium position harmonically. Part A. Show that the structure factor S sub g must contain terms of the form f sub j exponential minus ig dot rj, the angular brackets exponential minus ig dot u, where the angular brackets denotes thermal average. So let's do this step by step. So let's start with part A. The position of an atom in the presence of thermal fluctuations is basically given by R of t equals Rj, the position of the jade atom, plus the fluctuating term u of t. So we can recall the geometrical structure factor. So let's recall that the geometrical structure factor is given by S sub g is equal to volume of the unit cell multiplied by the Fourier transform of the electron distribution, n sub g. It's an integral over one cell, n of r, e to the minus I g dot r d cube r. Okay, so that's basically the Fourier coefficients of the electron distribution multiplied by the volume of the unit cell. So for a basis that contains more than one atom, we can write n of r as sum over j equals 1 to s, the number of atoms in the basis, and j of rho, where rho is the relative position r minus rj, d rho is equal to dr, s is the number of atoms in the basis, and Rj is the position vector of the jade atom with respect to the corner. So position vector of the jade atom with respect to the reference atom and rho is the position vector with respect to the detector, remember. So this allows us to write the geometrical structure factor S sub g as sum j equals 1 to s integral over one cell and j of rho e to the minus I g dot for rho. For r we substitute rho plus r sub j, rho plus r sub j, d cube rho. So this formalism basically we can use to calculate the geometrical structure factor in terms of what we define as the atomic form factor. So S sub g can be written as sum j equals 1 to s, the integral and j of rho e to the minus I g dot rho d cube rho multiplied by e to the minus I g dot r sub j. This integral is performed on one atomic radius, and the parenthesis is called the atomic form factor of the jade atom in the basis. And having remembered this result, S sub g can now be written as sum j equals 1 to s, the atomic form factor of the jade atom e to the minus I g dot rj. Now we have a modification here. Rj is now becoming Rj plus u of t, our fluctuating term. We have the nominal position of the jade atom plus the fluctuation term. All right. So the geometrical structure factor S sub g then becomes sum j equals 1 to s f sub j e to the minus I g dot rj plus u of t. So if we open this up, this is going to be f1 times e to the minus I g dot r1 plus u plus dot 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 for the jade atom fj e to the minus I g dot rj multiplied with e to the minus I g dot u, and for the s atom in the basis f sub s e to the minus I g dot rs plus u. Okay, now if we use a thermal average, so using the thermal average, we have the thermal average of the geometrical structure factor is going to contain terms fj exponential minus I g dot rj. These are not fluctuating terms. Then we have the thermal average of the term exponential minus I g dot u and the rest of the terms. So we can see that we will have terms of this form when we take the thermal average, because the rest is not fluctuating in time. So the thermal average will have a contribution from the thermal average of exponential minus I g dot u. So that is because g dot rj is fixed in time. All right, let's move on to part B. Show that for small fluctuations, The series expansion of the term exponential minus ig dot u thermal average can be written as 1 minus 1 over 6 average value of u squared g squared plus other terms. Okay, so let's work on the series expansion of this term, average value of exponential minus I g dot u. So we can use the exponential e to the x around x equals 0. So this is a small fluctuation. This Taylor series is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus higher order terms. This is our Taylor series. So if we apply this here, we will have 1 minus I average value of g dot u, and then the next term minus 1 over 2 average value of g dot u squared, etc. So if you consider the average value of g dot u, thermal average, this is going to be 0. Why? Because u is a randomly fluctuating term, so its dot product with a given vector will have an average value of 0. So u is a random thermal displacement uncorrelated with the direction of the reciprocal lattice vector G. In K-space. Okay. Now we need to work on the average value of g dot u square. So furthermore, we need to evaluate the average value of g dot u square. That would be g squared, because g is not fluctuating in time, average value of u square, and average value of cosine square theta, because g dot u is magnitude of g, magnitude of u, cosine theta. So the task is now finding the geometrical average of cosine square theta. So what is the geometrical average? The geometrical average of cosine square theta over a sphere where we have all angles with equal probability. The probability of finding an angle theta, P of theta, is probability of finding an angle theta for a random distribution will be basically equal to 2 pi r sine theta multiplied with r d theta, that is the area covered by this angle theta for a small variation d theta, divided by the full surface area of the sphere. So this is assuming that all angles have equal probability. So it's just the ratio of the 2 pi r sine theta r d theta. This is our circular region, so you can have an angle, polar angle theta here. This has a radius r sine theta. 2 pi r sine theta is the circumference, multiplied by r d theta is going to be the area of this small region here, divided by the full surface area, 4 pi r square, where r is the radius. So this is basically dA divided by A. That's assuming all angles have equal probability. So this will be equal to 2 pi r square sine theta d theta divided by 4 pi r square. That's basically sine theta d theta divided by 2. So that's the probability of finding an angle theta, p of theta in the this is basically p of theta multiplied with d theta here. P of theta d theta, probability of finding an angle theta that is in the range theta in the interval theta to theta plus d theta. So that's basically what we're looking at here. So the average value of cosine square theta, which is what we need for a random thermal fluctuation, is integral over all possible angles theta. So if you go from 0 to pi, basically we are covering all possible regions, dA's here. So this is 0 to pi. Integral probability distribution p of theta d theta multiplied with cosine square theta. So this is basically our statistical definition of average. You multiply the function with the probability distribution of its variable. So this is going to be an integral from 0 to pi sine theta cosine square theta divided by 2 d theta. And in order to perform this integral, we let u is equal to cosine theta, du is equal to minus sine theta d theta. And this integral is going to become 1 over 2 integral when theta is 0, cosine 0 is 1, so u is 1. When theta is pi, cosine pi is minus 1. So integral from 1 to minus 1, u is equal to cosine theta, du is minus sine theta d theta. So this is going to be minus u square du. So that is minus u cube divided by 6, evaluated between plus 1 and minus 1. So that's going to give us minus 1 cubed minus 1. So with the minus sign we have 1 over 6. And then minus becomes plus. U equals 1. So we have another 1 over 6. This gives us an answer 1 over 3. Okay. So basically, we have calculated the average value of cosine square theta to be 1 over 3. So we find that average value of time average of g dot u squared is g squared average value of u squared times 1 over 3. So we can substitute that to our Taylor series expansion average. So therefore, the average value of exponential minus I g dot u becomes 1 minus I average value of g dot u minus 1 over 2 g square average value of u square average value of cosine square theta higher order terms. So average value of g dot u, we have argued, is equal to 0 because you can take any possible angle with respect to this fixed vector g, and average value of cosine square theta, we're going to substitute 1 over 3. So we reach our final conclusion for the time average of exponential minus I g dot u exponential minus I g dot u is 1 minus 1 over 3 times 1 over 2, 1 over 6 g square average value of u square and higher order terms. So this is what we were asked to prove in part B. So show that the series expansion for small fluctuations will have terms of this form. Let's move on to part C. Show that the scattered intensity can be written as I0 times exponential minus 1 over 3 average value of u squared g squared, where I0 is the scattered intensity from the rigid lattice, that's without any fluctuations, and the exponential factor is called the Debye-Waller factor. Okay, so let's continue with part C. Now, the scattered intensity I is basically given by I proportional to number of unit cells, geometrical structure factor, absolute value squared. So this is basically capital N square, sum j equals 1 to s, fj e to the minus I g dot rj, average value of e to the minus I g dot u, absolute value squared, where capital N is now number of cells. So this is going to become N square absolute value j equals 1 to s fj e to the minus I g dot rj exponential minus 1 over 6 average value of u square g square to the power square. Okay, so you will notice that the Taylor expansion of exponential minus 1 over 6 u square g square for small values of u is basically the Taylor series expansion of an exponential minus 1 over 6 average value of u square g square for u small is 1 minus 1 over 6 u square g square and higher order terms 1 plus x squared over 2 factorial, etc. So this has the same form as exponential minus ig dot u. So that's why I can replace this average value of exponential e to the minus ig dot u with exponential minus 1 over 6 average value of u squared g squared, because it has the same Taylor series expansion. So this is the same. It's the same as average value of exponential minus I g dot u. All right. And so this allows us to replace, we can replace average value of exponential minus I g dot u with exponential minus 1 over 6 average value of u square g square. So if I go back to the intensity, then for the intensity, I have proportional to n square exponential minus 1 over 6 average value of u square g square square, and j equals 1 to s fj e to the minus I g dot rj parentheses squared. And this term basically we had in the summation, but it doesn't have any j in it, so there's no j index, so it can come out of the summation as a constant of the summation. So this comes out of the summation as a constant, so it doesn't belong to the summation. So the intensity then becomes I is proportional to n square, absolute value j equals 1 to s fj e to the minus I g dot rj squared. Then we have this term exponential, because we have exponential minus 1 over 6 and then squared, it becomes 1 over 3. Exponential minus 1 over 3 average value of u square g square. And we recognize that the term at the beginning is basically the intensity due to the rigid lattice. So finally, we reach the conclusion that the intensity of the fluctuating lattice is the intensity of the rigid lattice multiplied by an exponential factor, exponential minus 1 over 3, average value of square of the amplitude of fluctuations, reciprocal lattice vector magnitude squared. And this exponential factor that we have obtained here is called the Debye-Waller factor. So this is our correction to the intensity due to random thermal fluctuations of the atoms. This is our Debye-Waller factor. Okay, let's go back to problem part D. Here, so this is what we have shown. Here, average value of U square is the mean square displacement of an atom. Use equipartition theorem for the thermal average potential energy of a classical harmonic oscillator to show that the scattered intensity from HKL planes is given by I0 exponential minus KTG squared over m omega squared, where HKL are the indices of the reciprocal lattice vector G. This classical result is a good approximation at high temperatures and explains the following experimental findings. The scattered intensity decreases exponentially with temperature. The angular width of the reflected line is unaffected by finite temperature. The decrease in intensity of the scattered beam is more prominent for high index planes because G is increasing. You can see the experimental data below. You can see as the HKL values increase, we have a more prominent decrease in the intensity of the diffracted beams. Okay, so let's do the last part of the problem, part D. So here, average U square is the mean square displacement of an atom the thermal average potential energy average value of capital U of a classical harmonic oscillator in 3 dimensions is equal to 3 over 2 kBt by equipartition theorem. Why? Because we have x, y, and z in 3 dimensions. So we have 1/2 kx square, 1/2 ky square, and 1/2 kz square. So average value of the potential energy is 1/2 the spring constant average value of the u square. So this c is our spring constant. And that spring constant, according to Hooke's law, for a spring mass system, remember we have the equation of motion mx double dot equals minus cx. Angular frequency of oscillations is square root of c over m. So c can be replaced with m omega squared. So this is basically 1 over 2 m omega squared average value of u squared, which is basically equal to 3 over 2 kBt. So the 2's will cancel. So we can see that the average mean square displacement of an atom can be replaced by 3 kBt divided by m omega squared. So this is what we're going to do now. Alright, so for the last part, so if we substitute this result for average value of u square into the Debye-Waller factor, we obtain an intensity, the rigid lattice intensity I0 exponential minus 1 over 3, 3 kT Boltzmann constant times absolute temperature divided by m omega squared multiplied by g squared. The 3's will cancel, and therefore we have shown that the intensity is no fluctuations intensity I0 exponential minus kBt Boltzmann constant absolute temperature T reciprocal lattice vector g squared divided by m omega squared. So this was the suggested answer in part D. So to summarize, let's see. So this was what we were supposed to show. We have talked about the situation of having a random thermal fluctuation of atoms and the effect of that on the X-ray diffraction intensity. This was explained by Debye using Einstein's model of a solid, assuming that each atom fluctuates independently about its own equilibrium position harmonically, and the instantaneous position of an atom is the undisturbed position Rj plus the random thermal fluctuation. So what we have done here is basically we started out with this position vector and we calculated the geometrical structure factor from scratch, which is the volume of a unit cell multiplied by the Fourier coefficients of the electron distribution. And for a basis that contains more than one atom, for the electron distribution, we had sum over j equals 1 to s and j of rho. And basically, we have shown that using the atomic form factor here, we have sum over j fj e to the minus I j g dot rj, where rj is replaced by an rj plus a fluctuating term. Using thermal average, we have terms of the form average value of exponential minus ig dot u in the geometrical structure factor calculation. The average value of exponential minus ig dot u following the Taylor series of e to the x is basically 1 minus I average value of G dot U, which is 0 because U is a randomly fluctuating term, randomly fluctuating vector with all possible angles with respect to G. And then we have 1 over 2 average value of G dot U parentheses squared. So that means we have to calculate average value of cosine squared theta for a random distribution of angles. It's the ratio of the surface area of an angular region between theta and theta plus d theta, that's r sine theta 2 pi r sine theta r d theta, divided by the surface area 4 pi r squared, that's sine theta d theta over 2. So average value of cosine squared theta integrating over all possible polar angles from 0 to pi, covering all possible differential areas here, we obtain 1 over 3. So we substitute that for average value of cosine squared theta and find that the average value of exponential minus ig dot u has the form 1 minus 1 over 6 g squared average value of u squared plus higher order terms. Then the scattered intensity, where we have this term, average value of exponential minus ig dot u, can be written as exponential minus 1 over 6 g squared u squared terms. So why? Because the Taylor series expansion of this is identical to that of Taylor series expansion of exponential minus I g dot u. So for small u, this will have exactly the same Taylor series expansion. So we're replacing this term with this term. And having done so, we can take it out of the summation, and basically when we take its square, we have e to the minus 1/3 average value of u squared g squared. That's our Debye-Waller factor, the correction to intensity for random fluctuations. You can see that it exponentially decays with g, so higher HKL planes, higher HKL values will give a lower intensity, and also it's proportional to exponential minus 1/3 average value of u squared. So when we increase the amplitude of the random fluctuations, the intensity will also decrease. So using equipartition theorem for the potential energy of a classical harmonic oscillator in 3 dimensions, we can see that average value of u squared is 3 kT over m omega squared, where k is our Boltzmann constant, T is absolute temperature, m is the mass of the fluctuating atom, and omega is the angular frequency. Substituting that to the intensity, we see our new Debye-Waller factor is minus exponential minus kT g squared over m omega squared. So you see that with increasing temperature, we will see an exponential decrease in the intensity of the detected X-ray diffraction pattern.